and welcome to the next section on overfitting and underfitting. So in this section we'll have basically one learning goal, and that is understanding the definition of these two terms. So the intuitive definition, and also try to provide a rigorous mathematical definition of overfitting and underfitting, and then we'll play around a little bit with the terminology and try to characterize it and understand it as much as possible. I'll briefly discuss also countermeasures, especially to overfitting, but this will mainly be studied in a separate dedicated chapter, which is called regularization. Okay, so let's start with underfitting. So underfitting occurs if a model does not reflect the true shape of the underlying function. So I have an example down here. We have simulated data from two class-dependent Gaussian distributions. So we have a binary classification problem. We have class red here on the top. So these guys here are, let's say class +1, and we have class -1 down here. So these guys. Now, as I know that both of these classes are from a multivariate Gaussian, I also immediately know how the optimal decision boundary looks like. This will be a quadratic form. In a certain sense, we already know that quadratic discriminant analysis will provide us with the optimal decision boundary if you would fit it on enough data. Nevertheless, on the left-hand side here, I have now fitted a linear model to that data. So I think I fitted a linear discriminant analysis. I could have also used a linear support vector machine or a logistic regression model. And you can now see that obviously this model misclassifies more data than it should. So predictions would be less good as they could be. And that's kind of a relative comparison in terms of what would be possible with the usually unknown base optimal model. So for underfitted models, we would usually see a very high training error and a high testing error. But as I already tried to indicate a bit, it's a little bit hard to gauge this precisely to really figure out whether we could, in principle, reduce the training error and the testing error further by going to a different model class, because we really don't know usually what the optimal model class would be. So it's in practice potentially hard to detect. But in this case here, for the simulated data set, and for this, simulated situation, we know our optimal model, and I've also fitted here a quadratic discriminant analysis to these 200 training data points, and these this optimal decision boundary are basically estimated on an extremely large extra data set from the same distribution. You can see here that our underfitted model is worse in terms of training error, so it's 4 percentage points worse in training error, and it's also 4 percentage points worse in terms of test error. Now, overfitting occurs when the model reflects noise or artifacts in the training data. Well, when we overfit to the training data. This good performance on our training set does really not generalize to new data from the same distribution, which is ultimately what we are interested in on these new, fresh test samples. That's where we really want to optimize performance. So overfitting is usually visible through small training error at the cost of high test error. So predictions of overfitted models usually should not be trusted. We should avoid overfitting. There are many countermeasures in ML to handle overfitting. Currently, we mainly want to define it, and we want to talk a little bit about how we can detect it, or let's rather say understand the definition, what it means and how it works. Again, we have on the right-hand side our reasonable model, our quadratic discriminant analysis, and on the right-hand side, on the left-hand side, I have now fitted a certain support vector machine, so a kernelized support vector machine with an extremely small kernel width. Doesn't really matter what that means in detail here if you haven't seen it until here in the lecture. The point I want to drive home here is that this model has an extremely small training error, so it's basically learning all of the points by heart through a very, very extremely local model. It really tries to kind of capture every local peculiarity of the distribution, but this comes at the cost of not being able to generalize at all. So the model only has a high confidence, 1 millimeter next to each training observation, and then it doesn't really know how to predict if we move away only a little bit from a point, and that results in, for example, these points here, basically, I could say, I'm not sure whether I want to say by random chance, but basically arbitrarily being classified as class 2. And we can see that training error, when we compare that to our, basically we would say nearly base optimal model, is strongly reduced. So it looks much better on the training data, but in terms of test error, it actually fares considerably worse. So overfitting we can in practice usually detect very well, because we know how to estimate the generalization error, either through holdout splitting or what we will also discuss here in this lecture, through appropriate resampling techniques like cross-validation or related techniques. Here's another example for regression. We've also seen this elsewhere in the lecture already. Super simple univariate example with a couple of points sampled from this underlying sinusoidal function here. That's the dotted curve. And I've now used polynomial regression of different degrees. So degree 1, so that's a linear model. This guy here, degree 3, which is a quite reasonable model. So it's not exactly the optimal, or there's no exact match now between this polynomial of degree 3 and the underlying sinusoidal function, but it's fairly close. And then we have straightforward overfitting for this polynomial of degree 9, where I'm nearly interpolating the noise of the sampled training data points. I've also provided here potential mathematical definitions for overfitting and underfitting to make the terminology more precise. Guess that's in general a good idea. I also tried to check as many machine learning books as I could and papers, but basically none of them provides a very rigorous definition of overfitting or underfitting. But I guess these definitions here are fairly close to what is usually semi-rigorously discussed in literature. So underfitting we could define for a given model f hat, for specific models, so I'm defining this here for model and not for a learning algorithm, by computing the difference between the generalization error of our base optimal model and the generalization error of our given model. So actually probably should be the other way around. I guess we should rather put a hat here and a star here, because that guy, I guess that's a little typo on the slides, because that guy will usually be larger, right? So that's the smaller of the two. And that does make sense, because I'm now measuring underfitting and overfitting basically as a continuous property. So the larger these terms here would be, the more evidence we would have for underfitting or for overfitting. And if this term here becomes quite large, this would mean that our current model at hand, f hat, is much worse in terms of generalization performance than the best model we could find, the base optimal model for that underlying distribution. Now overfitting I could define in a similar manner by now comparing the generalization error of our model at hand minus the training error, which I could also call the empirical risk of my model f hat. So I guess in this case it's without typo. So this guy here is usually going to be larger than the training error. And we have seen instances before. I've also copied our examples from a few minutes ago on this slide. So we can again see here the nearly base optimal model. We can see our underfitted model, and we can see our overfitted model, and we can now kind of check out whether our mathematical definitions are in line with our intuitive understanding from before. So let's do this with the underfitted model. So we can compare now the generalization error. So this guy here, that's 10, with the generalization error of our base optimal model. So this would be 4 points difference. And there would be, let's say, substantial evidence now for this model being underfitted. And we can also check this here for being overfitted. And we can see that our test error of our model, 13 percentage points, is 12 points larger than the training error. We could actually also check whether this guy here is overfitted. So for this, we would have to check the training error versus the test error. This difference here is much, much smaller. So not really. Unfortunately, for these two definitions, this right-hand side here would also be now underfitted, because if we compare now the generalization error, 13%, to the error of our base optimal model, there's also large difference. And I guess now we would have to, I don't know, say something like if it's overfitted, then it's not underfitted. So overfitting somehow has priority as a, I don't know, characteristic or something like that. We can also discuss a little bit where overfitting comes from and how this is usually influenced by characteristics of the available training data, its structure, and the complexity of the hypothesis space. So it's influenced by how complex, how large is our hypothesis space, how large is the capacity of our learning algorithm, how many training data points do we have available, how high dimensional is our feature space, and how large is the irreducible noise. So the larger this guy here is, the more overfitting, or the easier we could actually produce overfitting in our resulting model. The less training data we have, the easier it is to overfit. The higher dimensional our feature space is, the easier it is to produce overfitting. And if noise is there, that also usually results in a higher chance of overfitting. This implies that the more complex our hypothesis space is, the more data we actually need to tell candidate models apart, to really find, by evaluating candidate models through empirical risk minimization, models in the hypothesis space are the truly well-fitting, or let's rather say well-generalizing ones. The less data we have, so if we kind of turn that argument around, the less data we have, then the more we need to stick with really constrained, simple, restricted hypothesis spaces. And overfitting can also happen for linear models, which we might deem as being extremely reduced and extremely restricted. If this feature space is very high dimensional, that can happen easily if we do not have many observations in these high dimensional spaces, and we still have to do something then in this case is for a linear model. Maybe, for example, run feature selection, maybe run or add regularization to our linear model like the Rich or the LeSoux. This kind of, analysis discussion is also tightly connected to the bias variance noise decomposition of the generalization error, which we have also studied elsewhere here in this lecture. So I'll not kind of do this here again. Have a look at the other video for the bias variance decomposition of learning algorithms. Here's another very, very common way of discussing underfitting and overfitting. So very often we visualize it in this schematic plot here. So we put complexity of our model on the x-axis. This could also be number of training rounds, training iterations. This would be another way of visualizing that. And we put the error on the y-axis. And now usually we can see that there's a strong monotonic downward trend of the training error. So the larger we make the complexity of our hypothesis space, the more we can actually fit to the training data. And the easier we can drive our error on that training data downwards to zero. On the other hand, the same is not true for the generalization error. So in the beginning, our models might be not complex enough. So we might still underfit. And then at some point, the generalization error actually goes up. And here we would then be in the area of overfitting. And here, this might be the appropriate complexity or the optimal complexity of our model class at hand. Now, if we would go back to our definition before, this model here in this area might still be underfitted. It depends now a little bit how rich our hypothesis space is. So if our base error would be like that, so if this would be the error of the base optimal model, we would have basically found it, or let's say approximated it quite well in our given hypothesis space. If the optimal base error would be like that, we would still be underfitting at that point here. And some people actually, and that's what you find in many books, if you look, at sections there where they discuss overfitting, they basically define overfitting exactly through that, upwards movement here of the generalization error when complexity or training iterations are increased. How can we avoid overfitting? So there are a couple of ways, which are basically all methods of regularization, which means I will study them in a complete dedicated chapter because this is such an important component and part of machine learning. So we can, of course, use more or better data, increase our sample size, use better, more informative features. Of course, we all know this is not always possible. If it is not possible, we can also try to augment our data through, for example, image augmentation techniques. This is a very, very common approach, for example, in CNNs in deep learning. We can also try to constrain our hypothesis H rather directly by using less complex model classes, so linear models instead of, boosting or kernelized support vector machines or neural networks. And we can also use continuous forms of regularization. So many learners actually come with one or multiple hyperparameters that can constrain the complexity in a continuous manner of that class of models. Or you can use early stopping as another regularization technique. And in general, it's a good idea to apply something like Occam's razor in model selection. So if the generalization error is not strongly reduced, or let's say significantly reduced for a more complex class, then use the simpler model. Usually that results in better generalization performance on new data.